Hi there, this is Yuan Chen, a PhD student with Monash University. Today, I would like to present our work, MV-Split Efficient 3D Gaussian Splitting from Sparse Multiview Images. MV-Split essentially aims to tackle the task called Novel View Synthesis, or NVS. So NVS aims to represent the 3D synthesis. It takes as input the 2D images from observed viewpoints, and it outputs the 2D images from novel viewpoints or unobserved viewpoints. I think probably the most important, the most popular recent advance of novel view synthesis is 3D Gaussian splitting, or 3D-GS. It is very popular because it renders images with high visual qualities and it achieves real-time renderings. But 3D-GS comes with several limitations, and most of them are originated from the requirements of parsing optimizations. It requires, for example, it requires hundreds of images for each synthesis. It requires more than 10 minutes for the training of each synthesis, and it also requires to store more than 10 megabytes of the models. So take these bicycle things as examples here. It takes around 200 images, requires 50 minutes for the optimizations, and store more than 100 megabytes for the models. Uh, these limitations are tackled one by one in the past 1 to 2 years, but today we're more interested in a solutions that take into considerations of all these limitations here, which is feed-forward 3D-GS. So unlike parsing optimized 3D-GS that requires backward optimizations for each synthesis here, feed-forward 3D-GS aims to learn a general model, which takes as input the multi-view images and output the corresponding 3D-GS directly. So once the general model is trained during the testing for a given novel synthesis, this feed-forward model can output the 3D-GS by taking only 1 to 5 images, and it runs only one single forward pass to that. This is less than 100 milliseconds, and it does not require to permanently store the models here. So one of the key challenges of feed-forward 3D-GS is that how to accurately localize the 3D Gaussian centers. So for example, take these 2D observed yellow pixels here. All those red points, 3D points along the camera rays are the possible candidates, but the model needs to tell us which is the correct one that is correspond specifically to these 2D observed points here. So one solution is that we can directly regress this point out. But the problem is that lack of guarantee for robustness, and it may only work for those object-centric simple synthesis. Another solution is that we can predict a density distribution, so that we can sample the depths from this learn the density distributions here. Problem is that it is challenging to learn and may lead to unreliable visual and geometry qualities. So our solutions to this issue is MV-Split, which use feature matching as the key motivations and offers a simple but effective solutions and gives us better visual and geometry qualities. So in a nutshell, MV-Split aims to learn mappings from image to 3D Gaussian splits. So it takes as input the multiple images with the corresponding camera pose, and it outputs the pixel-aligned 3D Gaussians for the synthesis, so that we can render the predicted 3D-GS to get us novel view images here. So the key motivation of MV-Split is feature matching. So intuitively, you can understand it from the images here. Like if the blue points is located on the object surface, then when it is projected to the 2D images here, the projected region will look similar. On the other hand, if the projected regions look different, then basically implies that the points are on the empty space. So with this simple motivation, essentially leads to a more efficient model design, better geometry quality, better appearance quality, and better cross-dataset generalizations. So how to implement it? MV-Split gives us a solution of we implement it as a multi-view transformer plus a cost volume. So the overall MV-Split builds a cost volume representation to efficiently predict the Gaussians from sparse multi-view images in a single forward pass. But specifically for a given images, we put it into a multi-view transformer to get cross-view enhanced features, and this feature will be used to build up the per view cost volumes. And this cost volume will be refined by the following 2D UNet, and then we extract the depth map from the cost volumes and unproject it to 3D Gaussians so that we can render the views from these 3D Gaussians here. And the whole framework is end-to-end trainable and is trained with photometric losses only. Here we present the ablation study. If we remove the cross-view attentions, you can see that the blue line here, performance drops a bit, and it also becomes overfit as the training goes. This means that the cross-view attentions from the multi-view transformer is critical to the model robustness. And this is also verified by the visual results. We can see that the error maps of the ablative model is more obvious compared to the base model, the default model. And if we the second ablation, if we remove the cost volume here, you can see the gray line here, the performance drops significantly. It basically drops 4 dB in terms of PSNR, and it's also verified by the visual result here. We can see that the error maps here becomes more and more obvious here. And so basically it means that cost volume is the cornerstones to the success of the NVSPLAC. So thanks to the effective visual matching, compared to state-of-the-art, NVSPLAC achieves 10 times fewer trainable parameters and runs 2 times faster, and essentially it still offers us better geometry quality. So NVSPLAC reconstructed point cloud with much higher quality, and it also gives us cleaner depth map. It also gives better appearance quality on both indoor scenes and outdoor scenes. It also gives us better cross-data generalizations when trained on the indoor scenes. It can be tested on object-centric scenes and also outdoor scenes, both with higher quality. But there are still several limitations of NVSPLAC. First of all, it lacks of generation capability. It cannot handle it cannot handle occluded or unobserved region. It cannot model those refractive effects for those non-Lambert surface. And it is very challenging to scale up. It cannot be applied to complex scenes here. So here we present a preview of a solutions for all these limitations, introducing the NVSPLAC 360. So NVSPLAC 360 is an upgraded next generation model. So it is built on top of our NVSPLAC here, but it leverages the video diffusion models to help generate the content. So essentially, it can be applied to more complex instances with wider baseline input views. The paper and code will be available very soon. Stay tuned and see you in Europe's 2024. Our paper, code, and models are available on our GitHub project page. Feel free to scan the left-hand side QR code. And also, I focus on feedforward overview synthesis. If you're interested in my research, feel free to connect. Thank you very much for your listening.